Have you ever looked straight up at the sky and wondered what lies directly above the sun? It sounds like a simple question. After all, on Earth, every direction feels obvious. There is up, there is down, there is left and right. But once you leave our planet behind, those familiar directions begin to disappear. In space, there is no universal up, no cosmic ceiling, no floor beneath your feet. So if a spacecraft launched straight above the sun, where would it actually go? Would it leave the solar system? Would it eventually reach another star? Or would it simply continue into an endless ocean of galaxies? Tonight, on What If Beyond, we're going to challenge one of the most common assumptions people have about space. We'll discover why up and down don't really exist in the universe, what lies directly above and below the sun, and how our solar system is positioned inside the Milky Way. The answers are far stranger than they first appear. Before we begin, tell me in the comments, what time is it right now where you are? And which city are you watching from? And if you enjoy relaxing documentaries about space, astronomy, and the greatest mysteries of the universe, don't forget to subscribe to What If Beyond. Now, get comfortable and let's find out what really exists directly above and below the sun. For thousands of years, human beings believed the universe had a natural orientation. The ground beneath our feet felt permanent. The sky stretched above us like an enormous ceiling. Birds flew upward. Rain fell downward. Everything around us seemed to agree on one simple idea. There was an unmistakable direction called up. It is one of the first concepts every child learns. Look up, look down, stand upright, lie down. Our entire language is built around these directions. Even our thoughts often use them. Success is associated with going up, failure with falling down. Heaven is imagined above, the underworld below. These ideas feel so obvious that we rarely stop to question them. But the moment we leave Earth, something extraordinary happens. The universe refuses to cooperate. Astronauts aboard the International Space Station often joke about losing their sense of direction. A laptop may be floating upside down. Another astronaut enters the room from what appears to be the ceiling. Someone else is working on what looks like a wall, yet every one of them feels perfectly upright. How is that possible? Because in space, there is no universal up. There is no cosmic floor. There is no invisible force telling the universe which direction should be considered above. The only reason up exists on Earth is because of gravity. Gravity pulls every object toward Earth's center. If you stand anywhere on the planet, your feet naturally point toward the center of Earth, while your head points away from it. That direction feels like up. But imagine two people standing on opposite sides of Earth. To each person, they are standing normally. Neither feels upside down. Yet if you could look at both from space, you would immediately notice something fascinating. Their heads point in completely opposite directions. Each person's up is different. Neither direction is more correct than the other. Both simply point away from Earth's center. Already, our everyday understanding of direction begins to fall apart. Now imagine leaving Earth entirely. A spacecraft slowly climbs away from the atmosphere. The blue planet becomes smaller. Gravity weakens. Soon, Earth no longer dominates your surroundings. If you continue drifting farther into space and turn the spacecraft upside down, nothing changes. You do not fall. Your coffee does not spill. Your body does not suddenly know which way is correct. Because space itself has no preferred orientation. The universe does not contain giant arrows pointing upward. There is no north for the cosmos, no ceiling stretching across the galaxies. only objects floating within gravity fields. This idea is surprisingly difficult to accept because our brains evolved on a planet. Every instinct we possess depends on gravity. Balance, walking, running, looking toward the sky. Everything assumes one stable direction. Astronauts must actually retrain their brains after arriving in orbit. During their first days aboard the International Space Station, many become disoriented. They accidentally float into equipment. They lose track of where they left objects. Sometimes they even become slightly nauseous because the inner ear can no longer determine which way is down. Eventually, something remarkable happens. Their brains adapt. Instead of relying on gravity, they begin using the spacecraft itself as a reference. A wall becomes the floor. The ceiling becomes another wall. If the entire station rotates 90 degrees relative to them, they simply adjust again. Inside the station, up becomes whatever direction they choose. There is no correct answer. Now imagine removing even the spacecraft. You are floating alone between Earth and the Moon. Nothing surrounds you. No floor, no ceiling, no nearby planet, no horizon. Only stars in every direction. Ask yourself a simple question. Which way is up? There is no answer. You could rotate continuously forever, and nothing in the universe would tell you to stop. Every direction would look equally valid. This is one of the strangest consequences of living in three-dimensional space. Without gravity or nearby landmarks, orientation becomes meaningless. This leads directly to the question that inspired this documentary. What exists directly above the sun? At first glance, the answer seems obvious. Surely if we point straight upward from the sun, we must eventually reach something. Perhaps another star, another galaxy, or maybe the edge of the universe itself. But before answering that question, we have to ask something much more important. Above, according to whom? The sun itself does not possess a universal top. From Earth's perspective, we often draw the solar system like a flat diagram. The sun sits in the middle. Mercury circles closest. Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, everything appears neatly arranged along one horizontal plane. It almost resembles a vinyl record floating through space. Because we see diagrams like this from childhood, many people imagine the solar system as if it were lying perfectly flat inside the universe. But that picture can be misleading. The planets do orbit within roughly the same plane. This happened because they formed from a rotating disk of gas and dust over 4.5 billion years ago. As gravity pulled material together, most of it naturally settled into one broad disk. The sun formed in the center. The planets formed inside the remaining material. That common origin explains why nearly every planet travels around the sun in almost the same direction and within nearly the same plane. Notice the word almost. Even inside our own solar system, the planets are not perfectly flat. Mercury's orbit tilts slightly. Mars has a different inclination. Pluto, although now classified as a dwarf planet, follows a dramatically tilted orbit compared with the major planets. Thousands of asteroids and countless comets travel in every imaginable direction. Some dive steeply above the planetary plane. Others pass far below it. Long-period comets arriving from the distant Oort cloud can approach the sun from virtually any angle. To one of these comets, the idea of above the solar system would make little sense. Its orbit may arrive almost vertically compared with Earth's. Already, even our own planetary neighborhood refuses to remain perfectly flat. Now zoom out. The solar system itself is moving through the Milky Way. It is not sitting still like a record on a table. It races around the center of our galaxy at nearly 830,000 kilometers per hour. Every planet follows the sun. Every asteroid, every comet, every spacecraft, everything bound to our star travels together. Imagine drawing a line directly above the sun. As soon as 1 second passes, the sun has already moved. 1 hour later, it occupies a different position. 1 year later, it has traveled millions of kilometers through the galaxy. Your imaginary line is no longer pointing toward the same region of space. The target continuously changes. The universe is dynamic. Nothing waits patiently while you define directions. Suppose you launched a spacecraft directly above the sun using today's orientation. Within days, the solar system itself would already have moved. Within centuries, nearby stars would shift positions. Within millions of years, the sun would occupy another region of the Milky Way. The spacecraft's path would no longer appear vertical from the solar system's new location. Even the question itself changes with time. This reveals something profound. Directions in space only have meaning relative to something else. You can travel north on Earth because Earth has a rotational axis. You can travel away from the sun because the sun provides a reference point. But there is no universal coordinate system labeling one direction as permanently upward across the entire cosmos. Astronomers do use coordinate systems, of course. They must. Otherwise, mapping the sky would be impossible. One common system uses Earth's equator projected into space. Another relies on the plane of the Milky Way. Others use distant quasars as nearly fixed reference points. These systems are incredibly useful. But they are human tools. Nature itself does not recognize one of them as the correct orientation. Change your reference frame, and up changes with it. Imagine standing beside someone on Earth. Both of you agree which direction points upward. Now imagine someone standing on Mars. Their up points away from Mars. It is completely different from yours. An astronaut orbiting Jupiter has another orientation. Someone living on a hypothetical planet orbiting Alpha Centauri would use yet another. Each observer constructs their own local version of up and down. The universe allows every one of them simultaneously. This is why astronauts often laugh when journalists ask whether they sleep upside down in space. The question has no meaning. Inside the spacecraft, every wall can become the floor. Every ceiling can become the wall. The only thing that matters is convenience. Human intuition struggles because we evolved in one gravitational environment. Space demands a completely different way of thinking. And once we finally accept that there is no universal up, an even stranger question appears. If above the sun has no absolute meaning, then what actually surrounds the sun in every direction? The answer is far more fascinating than simply saying empty space. What surrounds the sun in every direction is not a simple emptiness. The solar system may look like a flat collection of planets when seen in diagrams, but the region controlled by the sun is truly three-dimensional. Above the planetary plane, below it, and far beyond the paths of the known planets, the sun extends its influence into space. It does this through gravity, through radiation, through magnetic fields, and through a constant stream of charged particles flowing outward from its atmosphere. This flow is known as the solar wind. The sun is not a silent sphere shining at the center of the solar system. Its outer atmosphere is continuously escaping. Electrons, protons, and other particles move away from the Sun in every direction, traveling far beyond Earth, Mars, Jupiter, and Neptune. These particles create an enormous bubble surrounding the solar system. This bubble is called the heliosphere. The planets do not simply orbit the Sun inside empty space. They travel inside this vast solar environment. Earth is protected partly by its magnetic field, which deflects much of the solar wind around the planet. But the solar wind still affects us. It creates auroras. It can disturb satellites. It can influence radio communication. Powerful eruptions from the Sun can send clouds of charged material toward Earth, producing geomagnetic storms. The same solar activity spreads above and below the planetary plane. There is no calm ceiling above the Sun, no quiet floor below it. There is solar wind everywhere. But the flow is not identical in every direction. The Sun rotates. Its magnetic field twists as the solar wind moves outward. This creates an enormous spiral structure across the solar system. The magnetic field becomes wound into a shape often compared with the pattern produced by a rotating garden sprinkler. As the Sun turns, magnetic field lines are carried outward through space. The result is a vast rotating magnetic environment. A spacecraft moving above the Sun would pass through this invisible structure. It would encounter changes in particle density, magnetic direction, radiation, and solar activity. The journey would not look dramatic through a window. The surrounding region would still appear dark, but instruments would reveal that the spacecraft was moving through a restless environment. The solar wind can behave differently near the Sun's poles than near its equatorial regions. This is important because most planets travel near the Sun's equatorial plane. Nearly all our traditional exploration has taken place close to that broad disk. Humanity has viewed the solar system mainly from the side. We have sent spacecraft outward toward planets. We have crossed the orbits of giant worlds. We have traveled beyond the outer planetary region. But traveling far above or below the Sun is far more difficult. The reason is not that an invisible barrier prevents us from going there. The problem is orbital motion. Every spacecraft launched from Earth already carries Earth's enormous sideways speed around the Sun. Earth moves around its star at nearly 30 kilometers per second. A rocket does not begin from rest relative to the Sun. It begins while already moving rapidly within the planetary plane. To travel directly above the Sun, the spacecraft must change the direction of that velocity. That requires an enormous amount of energy. Launching away from the Sun is difficult. Turning a horizontal solar orbit into a steep vertical one can be even more demanding. Imagine a car racing along a highway. Moving slightly left or right is easy. Turning instantly upward into the sky is not. A spacecraft faces a similar problem, although there is no road and the physics involves orbital energy rather than wheels. Rocket fuel must change velocity. The larger the change, the more propellant is required. This is why most spacecraft remain relatively close to the ecliptic plane, the broad plane defined by Earth's orbit around the Sun. The planets are found there. Launch energy is used efficiently there. Gravity assists from planets are available there. Leaving that plane requires special mission design. One spacecraft did make an extraordinary journey over the Sun's poles. The Ulysses mission was launched to study the heliosphere from high solar latitudes, but it could not simply fly straight upward from Earth. Instead, it traveled toward Jupiter. The giant planet's gravity bent the spacecraft's path dramatically, pushing it into a steep orbit that carried it above and below the Sun. Jupiter acted like a gravitational ramp. Without that planetary encounter, Reaching such an orbit would have required far more fuel. Ulysses revealed that the Sun looks different when explored from outside the familiar planetary plane. It measured solar wind from polar regions. It studied the Sun's magnetic environment. It showed that the heliosphere changes over the solar cycle. The mission helped humanity observe the solar system from an angle that most planets never experience. This raises an interesting question. If we could rise far enough above the Sun, what would the solar system look like? At first, Earth's orbit would appear as a broad curve. The paths of Venus, Mars, Jupiter, and Saturn would form nested rings. The planets themselves would be tiny. From a great distance above the plane, the solar system might resemble a mechanical clock. Worlds moving around a bright center. Asteroids concentrated into a wide belt. Comets following more elongated paths. The flat structure would become obvious, but it would also become clear that the solar system is not perfectly flat. Mercury's orbit would appear slightly tilted. Some asteroids would move above and below the main plane. Pluto and many distant objects would follow noticeably inclined paths. Long-period comets would approach from nearly every direction. The farther outward we looked, the less disk-like the system would become. The inner solar system formed from a flattened rotating disk, but the distant Oort cloud may surround the Sun more like a sphere. This hypothetical reservoir of icy bodies lies far beyond the planets. Its objects are believed to occupy orbits with many different inclinations. Some circle above the planetary plane, others below. Some may travel in directions almost perpendicular to Earth's orbit. This means that if a spacecraft traveled directly above the Sun for a very long time, it might eventually pass through the domain of distant comets, not a crowded shell. The objects would be separated by immense distances. The spacecraft could cross the region for thousands of years without passing close to anything large, but the Sun's gravitational influence would still extend there. Above the planets does not mean outside the solar system. The Sun's domain is not a thin disk. It is a vast gravitational volume. The same is true below the Sun. Traveling downward relative to the planetary plane would not lead to a different kind of universe. There would be no lower cosmic region, no underside of the solar system. The spacecraft would encounter the same broad categories of material: solar wind, magnetic fields, dust, rare atoms, cosmic rays, distant comets, and eventually the wider environment between stars. The terms above and below only describe opposite directions relative to the chosen plane. They do not describe fundamentally different parts of reality. Still, those directions are scientifically valuable. Looking above the Sun can reveal things hidden when we remain inside the planetary disk. One example is interplanetary dust. The inner solar system contains tiny particles produced by asteroid collisions, comet activity, and other processes. These grains reflect sunlight, creating a faint glow known as zodiacal light. From Earth, this light can appear as a subtle triangle rising from the horizon under very dark conditions. It traces material concentrated near the ecliptic plane. A spacecraft moving high above that plane would leave much of the dust behind. Its view of the distant universe could become clearer. Many astronomical observations are affected by foreground dust. Sunlight reflected from nearby particles can hide faint cosmic signals. A telescope located far from the ecliptic could study distant galaxies with less interference from the glow surrounding the inner solar system. This is one reason scientists sometimes imagine future observatories positioned above or below the planetary plane. The view would not be blocked by a physical wall. it would simply contain less local dust. The darkness could become cleaner, more transparent, better suited for measuring extremely faint light from the early universe. But reaching such a location would remain expensive. A mission would need powerful propulsion or carefully planned gravity assists. It would also need communication across enormous distances. Power would become more difficult as sunlight weakened. The scientific benefit would need to justify the complexity. The Sun's polar regions themselves are also important. The Sun possesses north and south poles because it rotates around an axis. But these poles are not quiet frozen caps like those on Earth. They are regions of plasma, magnetic activity, open field lines, and changing solar wind. The Sun's magnetic field reverses approximately every 11 years as part of its activity cycle. Its north magnetic pole becomes south. Its south becomes north. The entire magnetic structure reorganizes. Sunspots increase and decrease. Solar eruptions become more or less frequent. The corona changes. The heliosphere responds. If a spacecraft remained above one solar pole for decades, it would watch the magnetic identity of that region transform. What we call north would remain the geometric pole of rotation, but magnetically, its role would reverse. This reminds us that even a clearly defined direction can contain changing physical meaning. The Sun's poles may also provide valuable information about its interior. The visible surface rotates at different speeds depending on latitude. The equatorial regions rotate faster than the higher latitudes. The Sun is not solid. It is made of plasma. Different regions can move at different rates. This differential rotation helps twist magnetic fields. It contributes to the activity that produces sunspots, flares, and coronal mass ejections. Observing the poles more directly could improve our understanding of how this solar dynamo works. From Earth, the poles are difficult to see clearly because our planet orbits close to the Sun's equatorial plane. We view the Sun mostly from the side. The polar surfaces remain foreshortened. Important structures become difficult to measure. A spacecraft above the Sun could look directly downward at a pole. It could map magnetic fields, track flows, observe polar coronal holes, study how the regions change throughout the solar cycle. Such observations would help scientists predict solar activity more accurately. That prediction matters because modern civilization depends on technology vulnerable to space weather. Satellites orbit Earth. Astronauts travel beyond the atmosphere. Power grids connect continents. Navigation systems rely on precise timing signals. A major solar eruption aimed toward Earth can disturb these systems. Understanding how the Sun's global magnetic field develops could improve warnings. A journey above the Sun is therefore not only an abstract exploration of direction, it could protect life and technology near Earth. But what would happen if we continued farther? Suppose a spacecraft used an advanced propulsion system and moved thousands of astronomical units above the Sun. The planetary disk would shrink below. The heliosphere would become visible only through instruments. Eventually, the spacecraft would approach the boundary where the solar wind loses dominance. This boundary is not perfectly spherical. The Sun moves through the local interstellar medium. Its surrounding bubble may be compressed in some directions and extended in others. Magnetic fields and particle flows shape the outer boundary. The heliosphere may resemble a rounded structure with a complex tail or wake, although its exact global shape remains a subject of continued study. A spacecraft moving above the Sun could cross this boundary at a different location from Voyager 1 or Voyager 2. it would sample another part of the heliosphere. The particle environment might differ. The magnetic transition might have another structure. By comparing several exit points, scientists could build a three-dimensional map of the Sun's protective bubble. Today, our direct measurements come from only a few paths. It is like trying to understand an entire ocean by lowering instruments through two narrow points. We know much, but much of the global shape remains reconstructed through models and remote observations. A fleet traveling above, below, ahead of, and behind the Sun could reveal the heliosphere as a complete object. This would also help us understand how other stars protect their planets. Every star produces its own environment. Some have powerful winds, some erupt frequently. Some possess strong magnetic fields. Planets orbiting those stars exist inside astrospheres, the stellar equivalents of the heliosphere. The shape and strength of these bubbles may affect atmospheric survival and habitability. A planet without adequate magnetic or atmospheric protection may lose gas over time. A violent stellar wind can strip a world. By studying the Sun from every direction, we learn how stars interact with the planets around them. The question of what lies above the Sun therefore expands into a question about life in the galaxy. Does a planet's position relative to its star's magnetic field matter? Do stellar poles produce different radiation environments? Could planets in highly inclined orbits experience changing conditions? Could a civilization survive near an active star if its world repeatedly passed through dangerous magnetic regions? Our solar system provides one example. Other systems may be arranged very differently. Some planets orbit stars on steeply tilted paths. Some stars rotate with axes misaligned relative to their planets. Some systems contain planets moving in directions opposite to the star's rotation. The neat arrangement around the Sun is not a universal rule. Planetary systems can become disturbed by nearby stars, giant planets, or early gravitational interactions. A system seen from above may look chaotic. Orbits crossing, inclinations differing, worlds moving on eccentric paths. Our broad planetary plane is a consequence of formation and history, not an instruction followed by the entire universe. The Milky Way also has a plane. Its disk contains most of its stars, gas, and dust. The Sun lies inside that disk. The solar system's planetary plane is tilted relative to the plane of the galaxy. This means that traveling above the Sun's planetary plane is not automatically the same as traveling above the Milky Way. The two coordinate systems point in different directions. This is another reason the word up becomes confusing. Above Earth is defined by Earth's center. Above the solar system might be defined relative to the ecliptic. Above the galaxy is defined relative to the galactic disk. These directions do not align. A rocket launched perpendicular to Earth's orbit would not travel perfectly toward the Milky Way's north galactic pole. It would move through a direction angled relative to the galaxy. To travel directly above the Milky Way, the spacecraft would need to use the galactic plane as its reference. From there, the journey would become almost unimaginably long. The Sun is embedded within the Milky Way's disk. This disk is not paper-thin. It contains stars spread across a vertical thickness of many light-years. Gas and dust are concentrated near the middle. Older stars can travel farther above and below. A spacecraft moving toward the galactic pole would first leave the dense local plane. The bright band of the Milky Way would shift behind it. Dust would become less obstructive. From far enough away, the galaxy's spiral structure would begin to reveal itself. But reaching a true external viewpoint would take far longer than any current mission could survive. Even traveling at the speed of our fastest spacecraft, moving only a few light years, would require tens of thousands of years. To rise far enough above the galaxy to photograph its full shape could take millions of years. The spacecraft would need to cross distances beyond practical human travel. This is why every complete image of the Milky Way seen from above is a reconstruction or artistic visualization. No camera has left the galaxy and looked back. We infer the spiral structure by mapping stars, gas, dust, and radio emissions from within. Humanity lives inside the object it wants to observe. It is like trying to map an entire forest while standing among the trees. We cannot see the full shape directly, but we can measure directions and distances. Gradually, the hidden structure appears. If a traveler could rise above the Milky Way, the view would be extraordinary. The galactic disk would spread below like a luminous spiral. A central bar would cross the bright inner region. Dark dust lanes would wind through the arms. Blue star-forming regions would mark areas of recent activity. The solar system would be completely invisible. Even the sun would be too faint to identify, without precise coordinates. Earth's entire history would occupy one undetectable point inside the galactic light. Above the galaxy, the idea of up would once again dissolve. The traveler might call the direction away from the disk upward, but after rotating the spacecraft, the disk could appear overhead. Nothing physical would change. The word would remain a convenience. Beyond the Milky Way's visible disk lies its halo. This region contains old stars, globular clusters, hot gas, stellar streams, and a vast distribution of dark matter. Leaving the bright galaxy would not mean escaping its gravity. The dark matter halo extends much farther than the luminous disk. A spacecraft could travel through apparent emptiness while still remaining bound to the Milky Way. To escape completely, it would need enough speed to overcome the galaxy's gravitational pull. The journey above the sun would therefore become a sequence of expanding domains. First, the planetary plane, then the outer solar system, then the heliosphere, then interstellar space, then the vertical structure of the Milky Way, then the dark matter halo, then intergalactic space. At every stage, the meaning of location changes, but no stage contains a universal ceiling. There is always more space ahead, perhaps a globular cluster, perhaps a dwarf galaxy, perhaps nothing nearby for millions of light years. The exact direction determines what lies along the path. A spacecraft launched above the sun today might eventually pass toward a certain region of the galactic halo. But because the sun and stars move, the future geometry changes. A star that appears in the path now may no longer be there by the time the spacecraft arrives. At interstellar distances, aiming becomes a prediction of future motion. You do not travel toward where a star is. You travel toward where it will be. At galactic distances, the challenge becomes greater. The target moves, the spacecraft moves, the galaxy rotates, gravity bends the path. Even a direction defined perfectly at launch becomes a curve through space-time. There is no endless straight vertical line waiting in the universe. There is only a trajectory influenced by motion and gravity. This is the hidden truth behind the question. What lies above the sun? Not one object, not one destination, not one simple answer. There are layers of the sun's environment, magnetic structures, solar particles, dust, comets, interstellar matter, galactic stars, dark matter, and eventually the enormous spaces between galaxies. What you encounter depends on how far you travel, when you leave, and which reference plane defines the word above. The same is true below. The directions are different. The principle is identical. Space has no preferred top or bottom, only paths. And the farther we follow those paths, the more the familiar geometry of the solar system disappears behind us. From a distant enough viewpoint, the Sun becomes one ordinary star inside a galaxy containing hundreds of billions. Its poles lose their practical meaning. Its planets become invisible. The distinction between above and below collapses into one larger reality. The Sun is surrounded by universe in every direction, and no direction is more cosmic than another. Once we stop searching for a universal direction called up, the question becomes much more precise. Which version of up do we want to follow? We could travel above the plane of Earth's orbit. We could move above the Sun's equator. We could aim toward the North Galactic Pole, leaving the broad disk of the Milky Way. Each route points into a different region of space, and each one reveals a different layer of the universe surrounding us. For the deepest version of this journey, imagine choosing the direction perpendicular to the disk of the Milky Way. Instead of traveling toward the galactic center or outward through one of its spiral structures, our spacecraft turns toward the space above the galaxy. Astronomers call this direction the North Galactic Pole. The opposite direction is the South Galactic Pole. These names do not describe an absolute top and bottom. They simply define directions perpendicular to the Milky Way's disk. From Earth, the North Galactic Pole lies toward the region of the sky occupied by Coma Berenices. The South Galactic Pole points toward Sculptor. To a person looking from the ground, neither direction appears especially important. There is no giant arrow in the sky, no visible opening through which the galaxy ends, only stars and darkness. But these directions are valuable because they look away from the crowded plane of the Milky Way. When we observe along the disk, our view passes through large amounts of gas, dust, and starlight. The galaxy becomes a bright band because we are looking through a long section of its stellar population. When we look toward a galactic pole, we are looking through the disk's thickness rather than along its width. The path through the densest material is much shorter. The background universe becomes easier to see. This is why regions near the galactic poles are useful for studying distant galaxies. Less dust blocks the view. Fewer stars crowd the image. A telescope pointed there can look beyond the Milky Way more clearly. But a spacecraft traveling in that direction would first need to cross our local galactic environment. The Sun does not sit inside a completely uniform sea of stars. It occupies a complicated region shaped by ancient stellar activity. Around the solar system lies a low-density cavity known as the local bubble. This region extends across hundreds of light years in an irregular shape. It contains extremely thin, hot gas. The word bubble may suggest a smooth sphere with a clear surface. The reality is more complicated. The boundary is uneven. Nearby clouds of cooler material exist inside or near it. Other cavities and shells overlap. The structure may have been created by several supernova explosions that occurred millions of years ago. Massive stars lived in our galactic neighborhood. They exhausted their fuel. They exploded. Their shockwaves pushed gas away and heated the surrounding region. The stars are gone, but the space around the Sun still carries evidence of their deaths. Our planetary system travels through the interior of a structure formed by ancient supernovae. The night sky appears quiet, yet the environment around us was shaped by explosions powerful enough to destroy stars. A spacecraft heading toward the galactic pole would first pass through the heliosphere, then enter this local interstellar material. There would still be almost nothing visible through a window. The gas inside the local bubble is far too thin to resemble a cloud on Earth. Even a region called dense by interstellar standards would be a near-perfect vacuum in a laboratory. The spacecraft would not encounter fog. It would not experience aerodynamic resistance in the familiar sense, but instruments would detect particles, ionized atoms, dust grains, magnetic fields, high-energy radiation. The emptiness would have structure. Some regions contain warmer clouds of partially ionized gas. The solar system currently moves through one such local cloud. Its particles interact with the outer heliosphere as the Sun travels through the Milky Way. The surrounding interstellar conditions change. At another point in galactic history, the solar system may have passed through denser material. In the future, it may enter another cloud. The pressure surrounding the heliosphere could increase or decrease. Its shape might change. The protective solar bubble could become more compressed. Traveling above the Sun would allow a spacecraft to sample this surrounding environment directly. Instead of studying the local interstellar medium from inside the heliosphere, the vehicle could measure the gas beyond it from a completely different direction. How quickly do particles move? What elements are present? How strong is the magnetic field? How does the local bubble connect with neighboring cavities? These questions help scientists reconstruct the violent history of the region in which the Sun travels. As the spacecraft rises farther from the galactic plane, the types of stars around it begin to change. The Milky Way's disk contains several overlapping stellar populations. The thin disk holds most of the gas, dust, young stars, and active star-forming regions. This is where the Sun lives. It is where spiral structures are most visible. It is also where most of the bright blue stars are found. These massive stars burn quickly. They remain near the regions where they formed because they do not live long enough to travel very far. The thin disk is dynamic. Molecular clouds collapse, new stars ignite, supernovae disturb nearby gas, radiation creates glowing nebulae, planetary systems form inside disks around young stars. If our spacecraft traveled sideways through this region, it might pass near more stellar nurseries and dense clouds, but by moving vertically, it gradually leaves the most active part of the galaxy. The number of young stars decreases. The gas becomes thinner. The sky changes. Below, the Milky Way's disk begins to concentrate into a brighter band. Above, the view contains fewer nearby stars and more distant galaxies. The spacecraft enters the thick disk. This population contains many older stars, following orbits that carry them farther above and below the galactic plane. They generally contain lower abundances of heavy elements than stars formed more recently. Astronomers use the word metals to describe elements heavier than hydrogen and helium. A star with fewer metals formed from material that had experienced fewer previous generations of stellar enrichment. Older stars therefore preserve evidence of an earlier Milky Way. A spacecraft passing through the thick disk would travel among ancient suns. Some may have formed when the galaxy was still assembling. Their planets, if they possess any, could have experienced histories far longer than Earth's. A civilization around one of these stars could have appeared billions of years before humanity. Or the system may never have produced suitable conditions for life. Age alone does not guarantee biology, but the possibility reminds us that leaving the galactic plane is not simply entering emptiness, it is entering an older region of the galaxy. The Sun's neighborhood contains stars of many ages, yet higher above the disk, ancient populations become increasingly important. Some stars move on tilted or elongated paths, repeatedly crossing the galactic plane. They spend part of their orbits far above it, then return. The disk's gravity prevents most of them from escaping. It pulls them back. This would also affect our spacecraft. Launching perpendicular to the Milky Way does not automatically mean leaving the galaxy. The vehicle may escape the Sun and travel many light years above the disk while remaining gravitationally bound to the Milky Way. The galaxy's mass continues pulling on it. If the spacecraft lacks enough speed to escape completely, its upward movement gradually slows. Eventually, it reaches a maximum height. Then it begins falling back toward the disk. It may pass through the plane and rise on the opposite side. The journey becomes an enormous galactic oscillation. Up, slower, a temporary turning point. Then, down again. From the spacecraft's perspective, nothing announces the moment when rising becomes falling. There is no ledge, no visible ceiling. Its velocity simply changes under gravity. This is similar to throwing an object upward from Earth, but on a scale measured in light years and millions of years. The Milky Way acts as the gravitational world beneath the spacecraft. Its disk replaces the ground. But unlike a solid planet, the spacecraft could pass through the galactic plane without hitting a surface. It would move between stars and clouds, continuing toward the opposite side. A vehicle could cross the galaxy vertically many times if its orbit remains stable. The Sun itself participates in a smaller version of this movement. Our star does not stay exactly in the middle of the galactic disk. It travels above and below the central plane over immense periods. The entire solar system follows. Earth's position within the galaxy is therefore changing vertically, as well as around the galactic center. At one time, the Sun lies slightly above the plane. Later, it crosses through. Then it travels toward the other side. There is no permanent upper side for our system. What we call north and south remain coordinate labels while the Sun moves through the structure. The galactic disk contains enough gravity to influence objects far above it. To escape completely, a spacecraft near the Sun's position would need a velocity of several hundred kilometers per second relative to the galaxy. That is far beyond the speed of present interstellar probes. Voyager is leaving the planetary region, but it is not leaving the Milky Way. It will continue orbiting the galactic center. Even after escaping the Sun's strongest influence, it remains part of the galaxy. The spacecraft may drift for billions of years and still never reach intergalactic space. This reveals the true difficulty of going up. The first challenge is leaving Earth, then escaping the Sun, then escaping the Milky Way. Every larger structure contains a deeper gravitational well. A rocket can leave the ground and still remain in Earth orbit. A probe can leave Earth and remain in solar orbit. A craft can escape the Sun and remain in galactic orbit. Traveling away from one system does not mean escaping every system containing it. To rise permanently above the Milky Way, future technology would need to provide a much greater speed, perhaps advanced fusion propulsion, antimatter engines, laser-driven sails, or methods not yet invented. Even then, the journey through the galaxy's vertical structure would take an enormous amount of time. At 1% of the speed of light, crossing 1,000 light years would require about 100,000 years. The visible disk is much larger than this in width, though its main stellar layers are thinner vertically. A human crew could not complete such a journey in an ordinary lifetime. The spacecraft would need to support many generations, or carry people in some form of suspended state, or operate without humans. Robotic explorers are far more realistic. A machine does not need breathable air. It does not experience loneliness. It can be designed to sleep for long periods and awaken near targets. But no machine built today can be guaranteed to function for hundreds of thousands or millions of years. Radiation damages materials. Dust impacts surfaces. Electronics degrade. Power sources weaken. Information storage can fail. A galactic escape probe would need to become one of the most durable objects humanity has ever created. It might repair itself, replace damaged components, use local resources, carry redundant systems, perhaps create copies of smaller probes along the journey. Such a mission would no longer resemble a traditional spacecraft. It would resemble a traveling technological ecosystem. Its creators might be gone before it crossed even a small fraction of the path. The mission would exist for future intelligences who may not speak our languages or share our civilization. Traveling above the galaxy requires thinking beyond individual lives. It requires designing for deep time. But suppose such a spacecraft existed. After leaving the thick disk, it would enter the stellar halo. Here, stars become far less common. Many are extremely old. Some belong to streams created when the Milky Way disrupted smaller galaxies. A dwarf galaxy approaches the Milky Way. Its stars once moved together inside a separate system. Then, tidal forces begin pulling it apart. The side nearest the Milky Way experiences a slightly stronger gravitational attraction than the far side. The smaller galaxy stretches. Stars are removed. Long streams form along its orbit. Eventually, its original shape disappears, but the stars remain as a faint ribbon circling the larger galaxy. The Milky Way's halo contains several such streams. They are evidence of ancient consumption. Our galaxy grew partly by absorbing smaller neighbors. The smooth-looking Milky Way is surrounded by the remains of destroyed systems. A spacecraft rising above the disk could pass through one of these streams. The stars may be widely separated, but their motion reveals a shared origin. They travel along related paths. Their chemistry may also match. By measuring their positions and velocities, astronomers reconstruct the dwarf galaxy that once contained them. A galactic halo is therefore not merely a faint outer region. It is an archaeological record. It preserves the history of mergers that built the galaxy. Some stars in the halo formed before the Milky Way reached its current shape. They contain very few heavy elements. Their chemical composition allows scientists to study the earliest generations of stars. Perhaps some were born inside tiny galaxies that existed before being absorbed. Their planets, if they formed, would have developed under conditions different from those around the Sun. Rocky planets require elements such as silicon, iron, oxygen, and magnesium. These became more common as stars created and released heavy material. A very ancient metal-poor star may possess fewer rocky worlds, but planetary formation is complex. Nature continues surprising us. The halo may contain environments not represented in our local neighborhood. Farther outward, globular clusters orbit the galaxy. These dense spherical systems contain hundreds of thousands or millions of stars. Some travel far above the disk. From a distance, a globular cluster appears like a bright compact sphere. Inside, stars can be much closer together than in the Sun's neighborhood. A planet there might see a night sky filled with brilliant points. Darkness could be rare, but close stellar encounters could disturb planetary systems. Radiation and ancient stellar remnants may create additional hazards. A spacecraft approaching a globular cluster would see the density of stars increase slowly. What appeared as one glowing object would separate into countless suns. The vehicle would enter a region older than most of the galactic disk. Some clusters may preserve stars formed more than 12 billion years ago. They are among the oldest structures in the Milky Way. A journey above the Sun could therefore become a journey into the galaxy's deepest history. But stars and clusters are not the only things occupying the halo. The region contains hot gas extending far beyond the visible disk. This circumgalactic medium is extremely thin, but its total mass may be enormous because it occupies such a large volume. Galaxies do not end where the starlight fades. They are surrounded by reservoirs of gas. Some material falls inward and may eventually support new star formation. Other material is pushed outward by supernovae, stellar winds, and activity near central black holes. The galaxy breathes, gas enters, gas leaves, gas circulates. This cycle connects the disk with the halo. Powerful explosions can drive heated material above the plane. The gas rises. It expands and cools. Some of it may eventually fall back. This process is often compared with a galactic fountain. The name creates an image of water rising and descending. The real fountain consists of plasma and gas moving across thousands of light years. Supernovae provide energy. Hot material escapes through channels in the disk. Cooler clouds condense. Gravity draws them back. The Milky Way recycles matter vertically. A spacecraft traveling above the Sun might encounter gas involved in this cycle, not as a dense stream. The particles would be incredibly sparse, but their speeds, temperatures, and chemical composition would reveal their history. Some atoms may have been forged inside stars, thrown into space by explosions, carried into the halo, cooled over millions of years, and now falling toward the disk where they could become part of another generation of stars. A single atom can cross the galaxy's vertical structure repeatedly. It may belong to a star, then a supernova, then hot halo gas, then a cool cloud, then a new star system. Matter does not remain loyal to one object. The galaxy continuously reuses it. High-velocity clouds also move around the Milky Way. These large concentrations of gas travel at speeds that do not match the simple rotation of the disk. Some may be material falling into the galaxy. Others may have been pushed outward and are now returning. Some could have been stripped from smaller satellite galaxies. Their exact origins differ. From Earth, we detect them through radio emissions, especially from neutral hydrogen. A spacecraft above the disk could study them from close range. A cloud may stretch across thousands of light years, yet remain so thin that the spacecraft passes through without any visible sign. Instruments would slowly report an increase in particles. The magnetic environment might change. The chemistry could reveal whether the gas originated inside the Milky Way or beyond it. These clouds may contribute fuel for future star formation. Without new gas, galaxies gradually exhaust the material needed to create stars. The halo therefore acts partly as a reservoir. The region that appears empty may influence the galaxy's long-term future. The Milky Way's center also produces enormous structures extending above and below the disk. One of the most dramatic examples is the pair of Fermi bubbles. These vast regions rise from the central area of the galaxy in opposite directions. They contain high-energy particles and emit gamma rays. Each extends for thousands of light years. Their origin may be connected to past activity from the supermassive black hole at the galactic center, or to intense episodes of star formation. They show that energy can travel vertically out of a galaxy on an extraordinary scale. A spacecraft leaving the disk above the Sun would not pass directly through the central Fermi bubbles because the Sun lies far from the galactic center. But from a sufficiently distant viewpoint, the bubbles would reveal that the Milky Way is not simply a flat spiral. It possesses gigantic structures extending above and below its central regions. The galaxy has a vertical life invisible in most familiar images. Illustrations often show only the disk. Reality includes fountains, bubbles, streams, clouds, globular clusters, satellite galaxies, and a dark halo. Above the galaxy is not empty, it is simply less luminous. Dark matter dominates the galaxy's outer gravitational structure. The halo is believed to extend far beyond the stars and gas. Unlike ordinary matter, dark matter does not form bright clouds or visible disks in the same way. It interacts mainly through gravity, as far as current evidence indicates. The spacecraft could move through vast amounts of dark matter without seeing or touching anything obvious. Particles may pass through the vehicle, through its instruments, through every atom of its structure. Unless dark matter interacts through a rare detectable process, the spacecraft would not know directly, but its trajectory would reveal the gravitational influence, the speed required for escape, the motion of nearby stars, the behavior of satellite galaxies. All depend partly on invisible mass. A traveler could be surrounded by the material controlling its path and remain unable to see it. This may be the strangest aspect of leaving the galaxy. The visible Milky Way could shrink behind the spacecraft. Its stars would form a magnificent spiral, yet the traveler would still remain inside a larger object with no visible boundary. The dark matter halo would continue far beyond the light. There would be no moment when a sign announced the end of the galaxy. No sharp surface. Gravity would gradually weaken. The density of halo material would decline. The Milky Way's influence would overlap with the influence of Andromeda, nearby dwarf galaxies, and the broader local group. Galaxies do not occupy perfectly separate territories. Their outer regions blend into shared gravitational environments. The question of where the Milky Way ends has several answers. The edge of the bright stellar disk, the limit of detectable gas, the outer reach of satellite galaxies, the boundary of the dark matter halo, the region within which objects remain gravitationally bound. Each definition produces a different size. A spacecraft traveling above the Sun would cross these boundaries one after another without seeing a clear line. Eventually, however, the Milky Way would become a distant object. For the first time, a camera could look back and capture our galaxy from outside. The spiral structure would be visible in full. A central bar, curving arms, dark dust lanes, glowing stellar nurseries, a faint halo, satellite galaxies nearby. The view would answer questions that humanity has studied from inside for centuries. How many major arms exist? How symmetrical is the disk? How does the central bar connect with the spiral pattern? What does the Milky Way truly look like in ordinary visible light? Astronomers currently reconstruct these answers through measurement. An external photograph would become one of the most important images ever created, but transmitting it back would take time. If the spacecraft were tens of thousands of light years away, the signal would require tens of thousands of years to reach Earth. The civilization receiving the image might be completely different from the one that launched the mission. Perhaps humanity would no longer exist, Perhaps Earth would no longer be inhabited. Perhaps the message would arrive at an automated receiver orbiting another world. Deep space exploration at this scale separates discovery from the discoverer. The people who ask the question may never receive the answer. A mission becomes a gift to the future. From outside the Milky Way, the Sun would be impossible to identify with an ordinary camera. It would blend into the light of the disk. Earth would vanish entirely. The entire solar system would contribute less than one invisible point. The direction once called above the Sun would now look like the route back toward one unnoticed star among hundreds of billions. This change in perspective would be profound. At launch, the Sun dominates the sky. Its gravity defines the journey. Its light powers the spacecraft. Its poles provide orientation. Far outside the galaxy, it loses every visible sign of importance. The Sun remains important only because the traveler remembers where it came from. Cosmically, it is ordinary. Home is not always the brightest place. It is the place connected to memory. Beyond the galactic halo lies intergalactic space. The density of stars falls dramatically. The distance between major galaxies becomes measured in millions of light-years. The nearest large destination, above or below the Milky Way, depends on the exact trajectory. A line toward the North Galactic Pole opens onto a sky rich with distant galaxies. Near that direction lies the Coma Cluster, an enormous collection hundreds of millions of light-years away. It is not directly waiting above the Sun like a ceiling. Its apparent alignment is simply part of our current perspective. A spacecraft following the general direction for an immense time might still miss the cluster because of motion, distance, and the narrowness of any exact trajectory. The cluster contains thousands of galaxies bound within a huge gravitational environment. Between the Milky Way and Coma lies an almost unimaginable expanse. Dwarf galaxies, faint gas, dark matter, smaller groups, cosmic filaments, large voids. The direction that seemed empty from Earth eventually intersects structures at many different distances. This is true everywhere in the sky. When we look between nearby stars, we often see distant galaxies behind them. Continue far enough along almost any direction, and the universe provides another layer. A star, then a more distant star, then the edge of the Milky Way, then a background galaxy, then another galaxy far behind it. Light from many distances overlaps in one small region of the sky. Our eyes flatten the three-dimensional universe into a two-dimensional image. Two objects appearing side by side may be separated by billions of light-years. The idea of traveling directly upward assumes the sky is a surface. It is not. It is a depth. A spacecraft follows one narrow path through that depth. Most objects seen near the path are not actually close to it. A planet visible beside the route may lie millions of kilometers away sideways. A star appearing directly ahead may possess motion carrying it out of the path before arrival. A galaxy may be so distant that expansion changes the meaning of reaching it. Direction is only the beginning of navigation. Distance and time determine what can actually be encountered. If our spacecraft continued beyond the Milky Way, it would remain inside the local group. The gravity of the Milky Way, Andromeda, Triangulum, and many dwarf galaxies shapes this region. The craft might escape one galaxy, but remain bound to the group. Again, the hierarchy continues. Planet, star system, galaxy, galaxy group. Larger cosmic structure. Each level requires more energy and more time to escape. The spacecraft could travel above the Sun for millions of years and still remain inside our local galactic neighborhood. To leave the local group, it would need to overcome the combined gravitational influence of its members. Andromeda would become an important force. The future merger of the two major galaxies would change the trajectory. A spacecraft launched today into what appears to be open intergalactic space could experience a different gravitational environment billions of years later. Its route would respond to the changing local group. The universe does not preserve the map used at departure. The destinations move, the roads evolve. The traveler must navigate a living cosmos. Beyond the local group, expansion becomes increasingly important. Nearby bound structures resist it. Very distant systems move away as the space between large-scale regions grows. A spacecraft cannot simply aim upward and assume every visible galaxy remains reachable. Some distant galaxies are already receding in a way that makes future travel impossible, even for light emitted from our region now. The observable universe includes places we can see only through ancient signals. Their current regions may lie beyond any journey that begins today. The sky contains images of destinations that no longer exist in reachable form. A galaxy may appear ahead, but what we see is its past. By the time a traveler could approach its location, the galaxy would have evolved and moved. At extreme distances, the growing space may prevent arrival entirely. This is where above the Sun finally loses all connection to a destination. The direction continues, but the objects along it belong to different eras. The nearby universe exists in a state close to the present. The distant universe appears younger. The farthest galaxies are seen before Earth formed. The oldest light comes from a time before stars existed. One line through the sky is also a line through history. Traveling along it does not move backward in time, but observing along it reveals the past. The farther we look above the Sun, the earlier the universe appears. A telescope pointed toward a galactic pole sees through the thinner part of the Milky Way and into deep cosmic history. It may detect galaxies whose light traveled for more than 10 billion years. Those photons began their journey while our own galaxy was still developing. They passed through expanding space, entered the Milky Way, crossed the solar system, and finally reached a detector near Earth. The direction above the Sun becomes an archive, not because the past is stored at a physical location there, because old light continues arriving from that direction. A spacecraft traveling toward the source would not reach the ancient galaxy as we see it. It would approach the galaxy's future state, assuming the region remained reachable. This difference between looking and traveling is essential. A telescope can explore the early universe in a single night by collecting old photons. A spacecraft cannot travel into that past. Distance allows us to observe history, but not enter it. The universe gives information without offering physical access. So, what truly exists directly above and below the Sun? Near the Sun, plasma, radiation, and magnetic structure. Beyond the planets, dust, comets, and the outer solar environment. Beyond the heliosphere, the local bubble, and interstellar clouds. Farther still, the thin disk, thick disk, ancient halo stars, stellar streams, hot gas, high-velocity clouds, and dark matter. Beyond the Milky Way, satellite galaxies, the local group, the cosmic web, galaxy clusters, and the expanding universe. There is no single answer, because the direction contains many distances. There is no cosmic ceiling waiting above us. There is layer after layer. And even the word layer is imperfect, because the structures overlap. Gravity reaches across them. Light crosses them. Matter circulates between them. The solar system belongs to the galaxy. The galaxy belongs to a group. The group belongs to the cosmic web. No border is completely isolated from what lies beyond. If we turned the spacecraft around and traveled below the sun, the journey would be equally rich. The local structures would differ. The exact stars, clouds, streams, and distant galaxies would change. But the principles would remain. The southern side is not a lower universe. It is another direction through the same cosmos. A civilization living on a planet with the opposite orientation might label our north as down. Their maps could place our familiar sky beneath them. Nothing physical would be wrong. Orientation belongs to the observer. The universe remains indifferent. This may be the deepest answer to the original question. We cannot simply go up, because up is not a destination. We can choose a direction. We can define it relative to a planet, a star, or a galaxy. We can build a spacecraft and follow that trajectory. But the moment we leave the reference object behind, the direction loses its ordinary meaning. What remains is motion through a three-dimensional universe shaped by gravity and time. The rocket in the familiar diagram appears to rise straight above the sun, but from another angle, it moves sideways. From a third angle, it descends. All views describe the same journey. None possesses a universal privilege. The spacecraft does not know whether it is rising or falling. It only measures its velocity relative to chosen objects. This is why space exploration requires coordinates rather than instinct. Astronauts cannot navigate by feeling which way is up. Computers track position relative to planets, stars, and reference frames. A mission is defined by vectors, speed and direction together. The universe is navigated through relationships. Perhaps future humans will become comfortable with this. Children born in rotating habitats may learn several meanings of up. Toward the floor created by rotation. Toward the center of a moon while visiting its surface. Toward the sun in navigation. Toward galactic north on star maps. They may switch between orientations as naturally as people on Earth switch between left and right. The fixed vertical world of our ancestors may become only one special case. Spacefaring civilization would need a more flexible sense of direction. It would understand that every world creates its own local sky. Every station creates its own floor. Every map chooses an orientation. No one lives truly above or below anyone else. They occupy different positions within shared space. This change may affect culture as much as navigation. Old ideas connecting height with importance could lose some of their force. The universe contains no throne at the top, no lower region of lesser worlds. A galaxy seen above Earth is not more elevated than one seen below. The categories are products of gravity and language. Cosmic perspective removes the hierarchy. Every direction opens onto equal depth. Every observer stands at the center of their own visible sky, and every center is temporary. The sun is not beneath the spacecraft, it is behind it. Then, after rotation, it appears above. The Milky Way begins as a band around the traveler. Later, it becomes a disk in the distance. Then a faint galaxy among others. Home changes from an environment into a point of light. Finally, it disappears. Yet the journey remains connected to that beginning. A spacecraft traveling beyond the galaxy carries the history of a species that once stood on a planet and asked what was above the sun. The question may have been based on a misunderstanding, but misunderstandings can lead to profound discoveries. Asking what lies above teaches us why direction is relative. It reveals the shape of the solar system. It exposes the difficulty of changing orbital planes. It leads us through the heliosphere. It opens the vertical structure of the Milky Way. It shows that galaxies possess halos larger than their visible disks. It connects local space with the cosmic web. A simple question becomes a map of the universe, and perhaps that is why it matters. Science does not always begin with a perfectly formed question. It often begins with curiosity. Then the question changes as understanding grows. What is above the sun? Becomes which reference plane do we mean? Why can't we go up? Becomes how much energy is needed to change orbital inclination? What waits beyond the planets? Becomes how far does the sun's influence extend? Where does the galaxy end? Becomes which boundary defines a galaxy? Every answer creates a more precise mystery. The universe does not become less wonderful when the original idea is corrected. It becomes deeper. There may be no cosmic up, but there are endless directions to explore. There may be no ceiling, but there are structures above the galactic plane that no human has ever visited. There may be no floor beneath the sun, but there are worlds, clouds, stars, and galaxies along every possible path. We are not trapped inside a flat solar system. We live within a three-dimensional cosmos extending around us without preference. The planets occupy one thin region. The galaxy occupies another broader plane. Beyond both lies space in every direction. And no matter which way we travel, the journey eventually teaches the same lesson. The universe is not arranged around human intuition. It does not need an up or a down. It does not need a top, a bottom, or a central viewpoint. It simply exists, deep, dynamic, connected, and open in every direction. If a spacecraft were launched directly above the sun, the most important moment would not be the launch itself. It would be the moment when the sun stopped looking like a place beneath the vehicle and began looking like one star among many. At first, the spacecraft would still belong clearly to the solar system. The sun would dominate the sky. Its light would illuminate every surface. Its gravity would control the trajectory. The planets would remain recognizable as members of the same system. But with distance, the familiar arrangement would slowly collapse into a single point. The orbit of Earth would become invisible. Jupiter would disappear into sunlight. Saturn's rings would no longer be resolved. The entire planetary system would shrink until it could not be distinguished from the star at its center. From far enough away, the solar system would stop looking like a collection of worlds. It would look like light. This is what every distant planetary system looks like to us now. A star, perhaps a slight wobble, a tiny dimming when a planet passes in front, a faint infrared excess from dust. The complexity remains hidden inside one point. A traveler leaving the sun vertically would witness this transformation directly. They would know that 8 planets, moons, asteroids, comets, oceans, atmospheres, and every human memory still existed behind them. But the universe would no longer display any of it. Home would become invisible before it became physically unreachable. The spacecraft would continue through the local stellar environment. No star would wait directly in front of it, like a destination painted onto the sky. The nearest stars are scattered through 3-dimensional space, a direction chosen perpendicular to one reference plane may pass nowhere near any of them. This is one of the least intuitive truths about interstellar travel. The sky appears crowded because stars are projected onto a distant background, but the line between them is usually enormous. A spacecraft can travel for light years Without approaching a star closely, what looks like a dense field from Earth becomes mostly darkness from within. The vehicle might pass through regions influenced by ancient stellar explosions. It could cross thin clouds of hydrogen. It might detect magnetic structures stretching across several light years. Cosmic rays would strike the spacecraft from many directions. Dust grains would become more dangerous because of speed. A particle smaller than a grain of sand could release significant energy if the spacecraft moved rapidly enough. Going upward through the galaxy would not require avoiding giant objects every few kilometers. It would require surviving a nearly empty environment for an extremely long time. Emptiness becomes a hazard through duration. A spacecraft designed for a journey lasting a few years can depend on stored supplies and known components. A spacecraft traveling for centuries must repair itself. A spacecraft traveling for thousands of years must replace parts repeatedly. A spacecraft traveling for millions of years must become almost independent from its original construction. Radiation slowly changes electronics. Microscopic impacts damage surfaces. Lubricants disappear. Materials become brittle. Data degrades. Even if the vehicle never encounters a planet, star, or large asteroid, time itself becomes the main obstacle. This creates an important difference between distance and survivability. The path above the Sun may be almost empty, but emptiness does not make it easy. There is no station where repairs can be made, no atmosphere to slow down in, no natural source of food, no nearby rescue. The spacecraft must bring a small civilization of systems with it: energy, navigation, manufacturing, protection, memory. It must remain able to understand its own mission long after the world that launched it has changed. A robotic craft could preserve instructions, but those instructions might become obsolete as the surrounding universe evolves. A stellar target may move. A galaxy may change position. A gravitational interaction could alter the path. The spacecraft would need to observe, calculate, and update its route. It could not simply follow one arrow drawn at launch. The farther it traveled, the more independent it would need to become. A mission above the Sun would slowly turn from exploration into autonomy. This would be especially important if the craft attempted to leave the Milky Way. The galaxy is not a passive background. It contains changing gravitational fields. Stars pass through the halo. Dwarf galaxies orbit and dissolve. Dark matter shapes trajectories. The spacecraft's path would curve even without engine thrust. To continue in the intended direction, it might need occasional corrections, but fuel is limited. Every correction has a cost. A small error early in the journey becomes a huge difference after millions of years. A change of only a fraction of a degree can move the spacecraft thousands of light years away from its original projected path. This makes precision essential, yet perfect precision is impossible. The positions and masses of all influencing objects cannot be known exactly. The future galaxy cannot be predicted in complete detail. Navigation over deep time would be probabilistic. The mission would not follow one guaranteed path. It would follow a range of possible futures. A sufficiently intelligent probe might treat the journey as a continuous decision. Observe, predict, correct, conserve resources. Choose new targets. Perhaps the original destination becomes unreachable. Perhaps a closer star passes near the route. Perhaps a newly discovered object becomes more valuable. The spacecraft could change the mission itself. This raises a strange question. At what point would the probe stop being merely a tool If it survives longer than the civilization that created it, modifies its plans, repairs its body, and decides which discoveries matter, does it still represent the original mission? Or has it become an independent traveler? The journey above the sun could extend beyond astronomy and into philosophy. Humanity may send a machine toward the galactic halo. The machine may carry our language, maps, and history. Thousands of years later, it may still remember Earth. Millions of years later, the solar system may be only an ancient coordinate. The probe may encounter worlds humanity never knew existed. No one on Earth may be waiting for the message. The explorer would possess knowledge with no guaranteed audience. This is one of the deepest challenges of interstellar exploration. Discovery traditionally assumes return. A sailor reaches a distant shore and comes home. A spacecraft visits a planet and transmits data. An astronaut collects samples and brings them back. But at galactic distances, return may lose meaning. The information may require thousands of years to arrive. The destination may be reached after the senders are gone. Exploration becomes an act performed for unknown descendants, or for the machine itself. Suppose the spacecraft reached a point several thousand light-years above the Milky Way. The galaxy would spread beneath it as a luminous disk. The view would finally reveal our galactic home from a perspective humanity has never possessed. But even then, the photograph would be incomplete. Dust would hide parts of the far side. Faint stars would merge into diffuse light. The outer halo would remain nearly invisible. Dark matter would not appear. The most important mass in the image would leave no direct visual trace. The galaxy would look beautiful, but the image would show only the luminous fraction. A complete map would require more than photography. The craft would measure stellar motion, gravitational effects, gas temperatures, radio emissions, X-rays, gamma rays, magnetic fields. The galaxy exists across many wavelengths and forces. A visible light portrait alone would be like photographing Earth at night and claiming to understand the entire planet. The spacecraft could watch supernovae flash inside the disk. From above, dust would obscure fewer regions than it does from Earth. A stellar explosion might appear and fade over months. Its expanding debris would become too small to resolve from great distance, but its light would carry information about the star's death. The craft might detect gravitational waves from compact objects merging somewhere in the galaxy. It could observe jets from the central region. It might measure gas falling into the halo or escaping from the disk. For the first time, the Milky Way could be studied as one external system. This would allow comparison with other spiral galaxies. From Earth, astronomers compare the Milky Way with distant galaxies while trying to reconstruct our own from inside. An external observatory would remove much of that uncertainty. It could measure the true brightness of the Milky Way, the exact distribution of star formation, the shape of the central bar, the number of major spiral arms, the degree of asymmetry caused by interactions, the connection between the disk and halo. The photograph would be emotionally powerful. The measurements would be scientifically transformative. Yet the signal delay would remain unavoidable. If the probe were 10,000 light-years away, its message would require 10,000 years to reach the solar system. The image arriving at Earth would show the Milky Way as it looked 10,000 years before the reception. The probe itself would already have traveled farther. Communication becomes a conversation with the past. Mission control sends a command. Thousands of years pass. The probe receives it. the probe responds. Thousands more pass. No human exchange can function this way. The mission must operate almost completely alone. This is why interstellar distance changes the meaning of control. Near Earth, a spacecraft can be commanded. Near Mars, there is a delay, but teams still plan operations. Near the outer planets, instructions take hours. Across light years, commands become historical documents. A probe leaving the galaxy cannot be managed in real time. It must be trusted. And trust in a machine over millions of years would require a kind of engineering humanity has never attempted. The craft may also face a cultural problem. What language should it preserve? Which version of humanity should it represent? A mission lasting deep time could not assume that future civilizations would understand modern symbols. Even Earth might forget the probe. Records may disappear. Languages may change. Political systems may collapse. The returning signal could be mistaken for an unknown extraterrestrial source. A message sent by humanity might come back to descendants who no longer recognize it. The distance above the sun becomes distance from history itself. For human passengers, the challenge would be even greater. A generation ship traveling above the galactic plane would need to function as a closed world. Children would be born who never saw Earth. Their descendants might know the sun only as an old star behind them. After thousands of generations, the original mission could become mythology. The concept of returning home might lose emotional meaning. The ship would be home. Its walls would define the environment. Its artificial gravity would define down. This is a beautiful reversal. The mission begins by asking what lies above the sun, because space has no fixed up. Then the travelers create their own up inside a rotating habitat. They manufacture direction. A rotating cylinder could spin to press people toward its inner wall. The wall becomes ground. The axis becomes overhead. Plants grow toward artificial light. Water flows according to rotation. Children develop balance inside a human-made gravitational environment. Their up would not point away from Earth or away from the sun. It would point toward the center of the habitat's rotation in the way their bodies experienced it. Direction becomes local again. Even in a universe without universal orientation, life creates practical orientation wherever it exists. A settlement on a moon has one down. A rotating station has another. A spacecraft accelerating steadily has another. During acceleration, passengers feel a force toward the rear of the vehicle. The rear becomes floor. If the engines stop, that floor disappears. Objects begin floating. If the craft turns and accelerates in another direction, up and down reverse. Future travelers may experience gravity not as a permanent feature, but as something engineered and adjustable. This could change human intuition. People born in space might understand direction as temporary from childhood. Their language could distinguish gravitational down, rotational down, navigational north, solar inward, and galactic north. They would not ask whether another station was above or below them without naming a reference. The confusion that makes the original question difficult today might feel obvious to them. Human thought would adapt to the universe. This has happened before. People once treated the horizon as the natural boundary of the world. Sailors learned that the surface continued beyond it. People once assumed Earth was fixed beneath the sky. Astronomy revealed that Earth moves. People once imagined a single universal time shared everywhere. Relativity revealed that measurements of time depend on motion and gravity. Intuition changes when experience expands. A spacefaring civilization would develop a three-dimensional culture. Maps would no longer place everything on flat surfaces. Routes would include inclination as naturally as distance. A destination could lie inward toward the sun, outward from it, above the ecliptic, below the galactic plane, or along a gravitational transfer path. The language of travel would become orbital. People might describe their homes by rotation period, orbital family, and reference plane. The idea of a universal top would seem as outdated as the belief that Earth is the center of everything. This change would not remove the emotional power of direction. Looking toward the sun could still mean looking toward human origins. Looking outward could mean looking toward uncertainty. Galactic north and south could become associated with exploration. But these meanings would be cultural, not physical. The universe offers directions. Humans create significance. If a generation ship continued above the Milky Way, eventually the galaxy's disk would become one feature in a wider sky. Andromeda would appear in another direction. The Magellanic Clouds would shift in perspective. Dwarf galaxies would reveal their true locations around the Milky Way. The local group would become three-dimensional in a way no Earth-based observer can experience directly. The travelers might aim toward a dwarf galaxy in the halo. These smaller systems can contain millions or billions of stars. Some are rich in dark matter. Others have lost gas through interactions with larger galaxies. A dwarf galaxy may appear insignificant beside the Milky Way, yet it can preserve ancient stars and early chemical histories. Exploring one could reveal what small galaxies were like before the Milky Way absorbed many of them. A spacecraft could approach a world whose sky is dominated by the Milky Way. From a planet in a nearby dwarf galaxy, our galactic home might appear as an enormous spiral stretching across the night. Its inhabitants, if any existed, might view the Milky Way the way humans view Andromeda: bright, distant, powerful, perhaps threatening. The perspective reverses again. The galaxy that seems like home from inside becomes a giant external object from elsewhere. Nothing carries a permanent identity independent of viewpoint. The sun is a dominant star from Earth, an ordinary point from the galactic halo, an invisible component from intergalactic distance. The Milky Way is the entire surrounding galaxy from Earth, a luminous disk from its halo, one member of the local group from farther away. Perspective does not change what the objects physically are. It changes which properties matter. This is why the question of what lies above the sun has so many answers. At one scale, the answer is the solar corona. At another, interplanetary space. Then the heliosphere. Then nearby stellar material. Then the Milky Way's vertical structure. Then the local group. Then the cosmic web. A direction becomes a sequence of changing contexts. There is no final object called the thing above the sun. There is only the next region along the path. The same is true of every direction. Point toward the galactic center, and the path passes through dense stars, dust, radiation, and eventually the region around a supermassive black hole. Point away from the center through the disk, and the spacecraft crosses spiral structures and outer stellar populations. Point above the disk, and it enters the halo more quickly. Point below, and it follows another halo route. Each direction reveals a different story. No direction reveals the entire universe. Even from far above the Milky Way, the traveler would not gain an absolute viewpoint. The galaxy might appear beneath the spacecraft, but this is only because the craft chooses to orient its windows that way. Rotate the vehicle, and the Milky Way moves overhead. Rotate again, and it appears beside the traveler. The physical relationship remains unchanged. Only the visual frame moves. This is the ultimate lesson of orientation. Objects have positions relative to one another. They do not possess universal places such as above and below. The terms become meaningful only when tied to gravity, rotation, or a chosen map. Yet the absence of universal direction does not create disorder. The universe remains measurable. A spacecraft can calculate its path. Astronomers can define galactic coordinates. Planets follow predictable orbits. Stars move through gravitational fields. The lack of absolute up does not mean every direction is the same in practical terms. A direction toward a star differs physically from one toward a void. A route through a dense cloud differs from one through thin halo gas. A trajectory near a black hole differs from one through quiet interstellar space. Relativity of orientation does not erase structure. It simply means the structure has no preferred top. This distinction is important. Sometimes people hear that direction is relative and imagine that location is meaningless. It is not. The spacecraft's coordinates matter. Its velocity matters. The surrounding mass matters. What disappears is only the idea that one orientation is universally correct. Nature does not label one side of the solar system as the roof. It allows us to choose a useful description. A future mission might deliberately travel far above the ecliptic to build a gravitational lens telescope. The sun's gravity bends light from distant objects. At extreme distances beyond the solar system, a spacecraft positioned along the line between the sun and a distant target could use this effect to magnify the target dramatically. The mission would need to travel hundreds of astronomical units away. Then it would move along a narrow focal region while keeping the sun aligned with a chosen exoplanet. The sun would act as a natural telescope lens. Such a mission could potentially reconstruct detailed information about a distant world. Cloud patterns, continents, oceans, seasonal changes, perhaps even signs of life. This would turn the journey above or below the planetary plane into a method of seeing another planet more clearly. The direction chosen would depend on the target. If the exoplanet lay near one part of the sky, the spacecraft would travel in the opposite direction, so the sun remained between observer and target. A different planet would require a completely different path. The solar system could someday send many probes outward in different directions, each using the sun as a lens for another world. They would form a scattered observatory extending far beyond the planets. No single up, no single down. Only carefully selected lines through space. This may be one of the most realistic reasons to send spacecraft far from the ecliptic. Not to search for a cosmic ceiling, to use the geometry of gravity. The sun's mass creates a tool larger than any telescope humanity could build directly. The universe offers structures that can be used if we understand them. Planets provide gravity assists. Stars provide gravitational lenses. Stable orbital regions provide places for observatories. Natural physics becomes part of engineering. The question, why can't we go up, may therefore be answered in two ways. We can. Nothing forbids it. But going far above a reference plane requires energy, time, and a reason worth the cost. Space does not resist the direction. Orbital mechanics does. A spacecraft begins with motion inherited from Earth. Changing that motion is expensive. But with advanced propulsion, planetary gravity assists, and long-duration missions, humanity can explore any direction. The difficulty is practical, not philosophical. One day, probes may surround the sun in 3 dimensions, some above the poles, some below, some ahead of the heliosphere, some in the distant wake, others far beyond the planets, aligned with nearby exoplanets. Together, they could map the solar system as a complete volume rather than a mostly flat collection of paths. They could monitor solar activity from every angle, measure the heliosphere's shape, track interstellar dust, observe the galaxy without as much zodiacal interference, use the sun's gravity to study distant worlds. This would transform our view of the cosmic neighborhood. Today, humanity occupies a narrow region. Most spacecraft remain near the ecliptic, because that is where Earth and the planets are. Our picture of the solar system is therefore shaped by one plane. Future exploration could break that limitation. The solar system would become a sphere of research. Its poles would be studied directly. Its boundary would be crossed at many points. Its three-dimensional structure would be measured rather than inferred. And when that happens, the original question may sound less mysterious. What lies directly above and below the sun? Not a hidden realm, not the edge of reality, not a different kind of space. What lies there is the same universe that surrounds the sun from every side. But seen from an unfamiliar angle, the same universe reveals different structures. That is the real value of going up. Not because up is special, because changing perspective is. In the end, the mystery of what lies above and below the sun is not solved by discovering one hidden object waiting in either direction. It is solved by changing the way we imagine space itself. From the surface of Earth, direction feels permanent. The ground beneath our feet defines down. The open sky defines up. The horizon separates the world we can touch from the universe we can only observe. Our bodies accept these directions without question, because gravity has shaped every moment of our existence. But those directions do not belong to the universe. They belong to Earth. They belong to one gravitational field, on one planet, during one brief period of cosmic history. The moment we leave Earth, the certainty begins to disappear. An astronaut floating in orbit can rotate until the planet appears above their head, turn again, and Earth appears beneath their feet. Nothing physical has changed. The astronaut is not falling toward a cosmic floor or rising toward a universal ceiling. Only the viewpoint has changed. This is the first lesson of space. Orientation is local. It depends on gravity, acceleration, rotation, or the coordinate system we choose. The sun also provides local directions. It rotates around an axis, giving it geometric north and south poles. The planets orbit within a broad plane left behind by the rotating disk of material from which the solar system formed. Astronomers can define a direction above that plane and another below it. These directions are scientifically meaningful, but they are not absolute. The plane of the solar system is tilted relative to the plane of the Milky Way. The galaxy has its own north and south. Earth has another. A spacecraft can be above one plane while remaining below another. There is no single orientation that every object in the universe must share. If a spacecraft traveled directly above the sun relative to the planetary plane, it would not enter a secret upper region of reality. It would first move through the environment created by the sun. The spacecraft would cross streams of charged particles carried by the solar wind. It would pass through magnetic fields twisted by the sun's rotation. It might move above regions where the planets and most interplanetary dust are concentrated. The paths of Mercury, Venus, Earth, Mars, and the giant planets would gradually flatten into a system of rings beneath it. From that unfamiliar angle, the solar system would finally reveal its broad architecture. The planets would appear to move around a shared center, Some orbits would be slightly tilted. Dwarf planets and comets would reveal that the system is less perfectly flat than simple diagrams suggest. Farther away, the spacecraft would approach the outer solar environment. The Sun's influence would not end at Neptune. It would continue through the Kuiper Belt, through the heliosphere, and toward the distant regions where icy bodies may surround the Sun in a vast cloud. The planetary plane would become less important there. Objects could approach from many angles. The outer solar system may resemble a three-dimensional swarm more than a flat disk. Traveling above the planets would therefore not mean leaving the solar system immediately. The Sun's gravity would still control the spacecraft. Its radiation would still arrive. Its solar wind would continue flowing outward until the surrounding interstellar medium became strong enough to resist it. Eventually, the spacecraft might cross the heliopause. The familiar particles of the solar wind would become less dominant. Galactic cosmic rays would become more common. The magnetic environment would change. Instruments would confirm that the spacecraft had entered interstellar space. But even then, the Sun would remain behind it. A bright star, a gravitational influence, the origin of the mission. The spacecraft would now be moving through the environment between stars. There would be no dramatic doorway, no glowing border visible through a window, only a gradual transition measured by instruments. This is true of many boundaries in space. They are real, but they are not walls. The heliosphere has no solid surface. The Milky Way has no sharp outer edge. A gravitational system slowly fades into the influence of larger structures. Human maps draw lines because lines help us understand. Nature often provides transitions instead. Beyond the heliosphere, the spacecraft would enter the local interstellar environment shaped by gas, dust, magnetic fields, and the remains of ancient stellar activity. The region around the Sun carries evidence of supernova explosions that occurred millions of years ago. Massive stars formed, burned through their fuel, and exploded. Their expanding shockwaves moved gas and heated the surrounding space. The stars disappeared. The structures created by their deaths remained. The spacecraft would therefore travel through a landscape formed before human beings existed, even though that landscape would appear almost completely empty. This emptiness would be deceptive. Particles would strike the vehicle. Radiation would damage materials slowly. Dust grains could become dangerous at high speed. Magnetic fields would influence charged particles. There would be physical conditions in every direction, even when no nearby object could be seen. If the spacecraft continued in a direction perpendicular to the galactic disk, it would begin leaving the youngest and most active region of the Milky Way. The bright band of the galaxy would gather behind it. Young stars and dense clouds would become less common. Older stars traveling on more inclined paths would remain. The craft would move into the thick disk and eventually toward the halo. From there, the Milky Way would begin changing appearance. The galaxy that surrounds us from Earth would slowly become an object. At first, it would remain too wide to understand from one view. Later, the disk would become clearer. The central region would appear brighter. Dust would trace dark structures. Stellar nurseries would mark parts of the spiral pattern. Globular clusters would move around the galaxy like ancient satellites. Faint streams of stars would reveal the remains of smaller galaxies torn apart by the Milky Way's gravity. For the first time, a traveler might see the history of our galaxy written across its entire structure. But reaching that viewpoint would require a journey far beyond anything current technology can achieve. human spacecraft have crossed the solar system. A few have entered interstellar space. None has traveled even 1 light year. The nearest stars remain thousands of years away at the speeds of existing probes. A journey far enough above the Milky Way to photograph its complete disk would require distances measured in thousands or tens of thousands of light years. The mission could outlast civilizations. It could outlast languages. It could outlast the species that began it. This creates a new meaning for exploration. A mission of that scale would not be created for the people launching it. Its discoveries would belong to an unknown future. A photograph of the Milky Way might take thousands of years to return after being transmitted. The image could arrive at a solar system inhabited by descendants who no longer recognize the names of the nations that built the spacecraft. Earth might have changed. Humanity may have spread to other worlds. The message could become a letter sent across deep time. Exploration would no longer be a conversation between mission control and a machine. It would be an act of trust between generations, separated by cosmic distance. The spacecraft itself would need to become something far more advanced than an ordinary probe. It would need to repair damage, manage power, protect information, correct its path, update its understanding of the stars around it. The map loaded at launch would gradually become outdated because the galaxy moves. Stars change position. Some die, others form. Dwarf galaxies shift along their orbits. The Milky Way and Andromeda continue approaching one another. A probe surviving for millions of years would need to treat navigation as a continuous process rather than a fixed route. It might discover that the original destination had moved. It might choose a more valuable target. It could become independent from the mission imagined by its creators. At some point, the machine might be the only surviving part of the civilization that sent it. It would carry records of Earth into regions where the sun could no longer be distinguished from surrounding stars. The probe would remember a home that the universe itself no longer displayed clearly. From outside the Milky Way, the sun would disappear into the combined light of hundreds of billions of stars. Earth would contribute nothing visible. Our oceans, continents, cities, and history would vanish into one faint point inside a spiral galaxy. The spacecraft would know where humanity began, only because that information had been preserved inside it. This reveals a profound difference between cosmic importance and personal meaning. The sun is not physically special among the stars of the galaxy. Earth is not visible on galactic scales, but the solar system remains meaningful because it is home. A place does not need to occupy the center of the universe to matter. Meaning is not measured by size. A tiny world can produce observers capable of understanding galaxies. A short-lived civilization can create a machine that travels for millions of years. A small question asked beneath one sky can lead toward the largest structures in existence. The question of what lies above the sun may begin with a misunderstanding, but it opens a path through nearly every scale of astronomy. It teaches us that the planets formed in a disk. It reveals why changing orbital inclination requires so much energy. It leads toward the sun's polar regions and the changing solar wind. It takes us through the heliosphere and into the local interstellar medium. It reveals the Milky Way's thin disk, thick disk, halo, gas clouds, ancient clusters, stellar streams, and dark matter. Then, it carries us outward into the local group and the cosmic web. One simple direction becomes an entire journey through the structure of the universe. The same would be true if we traveled below the sun. The particular objects along the path would change. different stars would appear nearby. Different interstellar clouds might be crossed. The spacecraft would move toward another part of the galactic halo. Beyond the Milky Way, it would face another section of the cosmic web. But nothing would make that direction physically lower. A civilization living on a differently oriented world might place our galactic south at the top of every map. Their children would grow up believing that direction was naturally upward. Their spacecraft would use coordinates that looked reversed to us. Neither civilization would be wrong. Maps choose orientation. The universe does not. This idea may become natural to future humans. People born in space habitats may grow up with several kinds of down. Inside a rotating station, the outer wall becomes the floor, because rotation creates an apparent force pressing residents toward it. Inside an accelerating spacecraft, the direction opposite acceleration becomes down. On the surface of the Moon, down points toward the lunar center. On Mars, it points toward the center of Mars. During free flight, down may disappear completely. A child raised in space may understand direction as something created by the local environment rather than a permanent feature of reality. Their language may be more precise than ours. Instead of saying something lies above them, they may say it lies away from the sun, toward galactic north, opposite the direction of acceleration, or outside the station's rotational axis. Human thinking would become more three-dimensional. The ancient idea of the sky as a ceiling would be replaced by an understanding of space as depth in every direction. This shift could change more than navigation. For much of history, humanity placed importance above and danger below. Palaces rose above cities. Heavens were imagined overhead. Dark worlds were placed beneath the ground. Space removes that hierarchy. There is no throne at the top of the cosmos, no lower half of the universe containing lesser worlds. A galaxy above Earth is not more elevated than one below it. Every observer sees a sky around them. Every world creates its own local vertical direction. Every civilization could believe it stands upright. The universe allows all of them to be correct at once. This does not mean direction is meaningless. A spacecraft must still know exactly where it is going. A path toward the sun differs from one away from it. A route through a dust cloud differs from one through a cosmic void. A trajectory near a star requires different protection from one passing through the galactic halo. Relative direction remains physically important. What disappears is only the claim that one direction is universally the top. The universe is organized through relationships, distances between objects, velocities relative to reference frames, gravitational fields, rotational axes, magnetic structures. A spacecraft navigates these relationships mathematically. It does not need a cosmic up. It needs position, velocity, time, and a defined target. Future missions may use this understanding to explore the solar system from completely new angles. Probes could travel above the sun's poles to observe its magnetic cycle directly. Others could cross the heliosphere in several directions and reveal its true three-dimensional shape. Observatories far outside the dusty planetary plane could search for the faintest galaxies and measure ancient cosmic light with less local interference. Some spacecraft might travel far enough to use the sun's gravity as an enormous natural lens. By aligning the sun with a distant exoplanet, a probe could use the bending of light to study a world many light years away. It might reconstruct clouds, oceans, continents, seasonal patterns, perhaps signs that the planet is alive. Such missions would not travel upward, because the direction is special. They would travel along carefully chosen lines because the geometry of the universe makes those locations scientifically valuable. That may be the most practical lesson hidden inside the original question. We are not forbidden from going above or below the sun. We can travel in any direction. The difficulty comes from orbital mechanics. A spacecraft launched from Earth inherits Earth's sideways motion around the sun. Changing that motion into a steep path away from the planetary plane requires enormous energy. Gravity assists can help. Advanced propulsion may make the journey easier. The universe does not block the route. Our current technology limits how efficiently we can follow it. One day, humanity may surround the sun with spacecraft operating far outside the planetary disk. The solar system would no longer be explored mainly as a flat collection of worlds. It would become a complete three-dimensional environment. We could observe the sun from every latitude, map the solar wind from multiple directions, measure the boundary of the heliosphere as a global structure, study comets approaching from distant orbits, watch the planets from above and below their paths. Our understanding of the solar system would change as dramatically as our understanding of Earth changed after the first photographs from space. The familiar would become new because the viewpoint had changed. This is what exploration does. It does not always discover an unknown object. Sometimes it discovers a new way of seeing something we thought we already understood. Earth became more fragile when seen as a small blue sphere. The solar system would become more complex when seen outside its broad plane. The Milky Way would become one temporary galaxy when seen from its halo. Every change of perspective removes one illusion. It also creates a deeper sense of wonder. So what truly exists directly above and below the sun? Near the sun, there is plasma, light, magnetic activity, and solar wind. Beyond the planets, there are small bodies, dust, and the distant domain of comets. Beyond the heliosphere, there are interstellar particles, magnetic fields, and the ancient scars of stellar explosions. Farther away lies the vertical structure of the Milky Way. Old stars, globular clusters, gas clouds, stellar streams, dark matter. Beyond the galaxy lies the local group, then filaments, clusters, voids, and galaxies extending toward the observable horizon. There is no single object waiting at the end. There may not be an end at all. There is only the next region, the next scale, the next version of the question. The sky is not a surface placed over our heads. It is every direction leading away from Earth. When we look upward, we are looking outward. Someone standing on the opposite side of the planet looks in the opposite direction and also looks outward. Together, humanity looks into the universe from every part of Earth's surface. Our combined sky surrounds the planet completely. The ground hides half of it from each individual observer, but the universe continues through the ground, beyond the planet, and into another sky. This is the final answer. There is no true above the sun. There is no true below it. There are only directions defined relative to objects, and each direction opens onto the same vast universe. A universe without a roof, without a floor, without a universal orientation. A universe filled with motion, gravity, light, matter, and distances beyond ordinary imagination. We began with a rocket rising above the sun. But from another viewpoint, the rocket moved sideways. From another, it descended. From the spacecraft itself, it simply followed a trajectory. All of these descriptions can be correct. The journey does not belong to one orientation. It belongs to space. And perhaps the most beautiful part of this discovery is that losing our familiar directions does not make us lost. It gives us more paths. No universal up means no direction is forbidden. No cosmic ceiling means exploration never ends at the sky. No absolute bottom means there is no lower boundary beneath creation. The universe remains open around us, in every direction, at every scale. And wherever humanity travels, we will carry our own sense of home, our own temporary horizon, and our own questions into the darkness. Because the cosmos has no top and no bottom, only endless directions waiting to be understood.